Interesting talk.
Thanks for the introduction, and my pleasure to visit CITA for the first time. So, because I had some toothache yesterday, so maybe my voice is a little bit low. But if you cannot hear clearly, just let me know. Okay. So this is the recording. This is.
You need a dentist, I should say. It's they're pretty reasonable in Canada.
Presumably it's
I once waited for 2 weeks to get back to Canada so I could come to my dentist.
All right, thank you. Yeah, so today I will talk about the recent work that with a number of collaborators, postdocs, and professors and students. We form a group at the IS, and we did data analysis, independent data analysis of the LIGO, Virgo strain data to look for astrophysical gravitational waves. So this is, I think this is something that quite different for us, quite different from what we did before. Just to start with some big picture to motivate this work. I think the major motivation, of course, is that people have LIGO Virgo has detected gravitational waves from astrophysical sources, and to people's surprise, it seems that in the universe, it's very common to have two binary black holes merging with one another and generate very powerful gravitational waves. So far, in this cartoon, people show the number of gravitational wave source detections by the LIGO Virgo collaboration, and then. From here, you can see that the majority of them are binary black hole mergers, and they seem to be made of very massive black holes, more massive than the other black holes people have discovered through electromagnetic waves. And then, of course, in addition to that, people have discovered a wonderful binary neutron star merger. And among the many other neutron stars people know from electromagnetic observations. But here, so basically the dominance of binary black holes as LIGO sources do not necessarily mean that they are physically the most abundant merger phenomenon, but it's rather because of the fact that the gravitational wave signal becomes much stronger if the sources are more massive, and therefore you have access to a larger detection volume. So here, what I show is at the current sensitivity level for LIGO Virgo, for mainly the two LIGO detectors, what is the horizon distance to different types of sources. So for binary neutron stars, because of the low masses, currently we can only see out to our cosmic backyard. So we can only see up to 100 to 200 megaparsec. But then for these massive black hole mergers, each of them weigh as heavy as 30 solar masses, we can already see out to cosmological distances, so a few gigaparsec, corresponding to redshift maybe from 0.2 to 0.5-ish. So I want to stress that basically we are already seeing the population of these binary black hole mergers as a function of redshift. And then we haven't, LIGO Virgo have not officially published neutron star black hole mergers, but the rumor came that they have detected one in the current run. So for these mergers, they will also be restricted to small distances. So I think currently people, yes?
For the neutron star black hole potential merger, because I know all this is very often stuff on Twitter, so like people are posting the events that are happening on Twitter with some preliminary, say, like false alarm rates and so on and so forth. Do you know what the explanations available for this potential?
So I think from LIGO spokesperson, so from one talk, the spokesperson said they have 3.5 detections. And 0.5 means that some of the detections, they are still unsure, what's the significance. But I think my comment is that for neutron star black hole, because if you want to really be sure it's neutron star black hole, you need to have some statement about the mass ratio. So you have to make sure that one of them is really a neutron star, cannot be a low mass black hole. So this requires pretty high confidence in the mass ratio measurement. And as I will show, actually mass ratio is a parameter that is not very well measured in gravitational signal. Yeah, so I would say it remains to see their paper to see eventually how confident they are. Because so far, none of the events had a successful electromagnetic follow-up. So for the binary black hole system, how do they form? Currently, people have classes of theories. People cannot make very precise predictions, but there are a number of general postulations. So one is that you just have a pair of massive stars, and they evolve in a way that they affect each other. And in particular, when one star expands to become a giant star, it's very common that the envelope of that star can engulf the other star. And then this is what people call common envelope phase. And then what happens next is not very certain, because people don't have direct observational evidence. But one possibility is that the core of these two stars, they spiral toward each other and giving off enough energy to unbind the envelope, but they don't necessarily have to end up merging with each other. So then they stay at a relatively small separation, allowing them to merge within Hubble time after both become black holes. So this is one straightforward, most straightforward way. But then the other possibility is that if you're in a very dense environment, then you could have dynamic capture. So for example, two black holes encountering each other, emitting gravitational waves and become bound. Or you could have single binary interaction. So in these cases, you can make sufficiently tight binary black holes, and they can merge within Hubble time. And then there's, in a more specialized environment, there may be other channels to form them. For example, people theorize that maybe surrounding supermassive black holes there is an accretion disk with a very high gas density. So then these massive black holes, they can interact strongly with the disk. They accreting matter efficiently, and then they grow quickly, and then they can also form pairs in the disk and merge. And of course, it is always possible that maybe the primordial universe leave us with some black holes. So all of these so far are possibilities, and we do not yet have very clear proof which channel is the dominant channel. So here, for binary black holes, just from the gravitational wave signal, here are the main pieces of information we can get. So we can measure the so-called chirp mass, which is some combination of the two component masses. So the meaning of this chirp mass is basically telling you how does the frequency of the gravitational wave evolves as a function of time. And then we can have some measurement of the mass ratio. But because to leading order, the gravitational wave form only depends on this chirp mass parameter. And this is some next to leading order effect. So we have relatively poor accuracy on the mass ratio measurement. So for example, currently, all the black holes we have detected are consistent with a mass ratio between 1 and, let's say, 0.5. So all of them, we cannot really tell if they are like 1 to 2 or they are equally massive. And then apart from that, we can measure a single parameter describing the spin. So each black hole, in principle, has a three-dimensional spin vector. But so far, the signal-to-noise we typically have allow us to measure only this particular combination, a mass-weighted average of the spin component parallel to the angular momentum vector. So this is called the effective spin parameter. And finally, we note that because we are detecting gravitational waves at cosmological redshift, so what we really directly measure is the multiplication of the intrinsic mass multiplied by 1 plus z. So I'll give a brief summary of what properties these LIGO binary black hole population exhibit. So first of all, they are really massive. Most of them are like at least 30 solar masses per component, and they are definitely systematically heavier than black holes inferred from X-ray binaries, Milky Way X-ray binaries. And also there is some evidence that we are not seeing very massive ones, more massive than, let's say, 50 solar masses. Although those signals should be loud enough to be detectable. So this may suggest that maybe there's a physical mass cutoff on the individual mass. And the majority of the binary black holes, they appear to spin slowly because most of them, the effective spin parameter is consistent with 0. Even if in a few cases not consistent with 0, they take low values instead of.
What can we say about the mass ratio distribution in the binaries?
For this Q. It's currently, I think, constraint is very weak because the posterior distribution for Q for each event is really wide. This is because this Q, once you fix M, this Q is not very effective at changing the waveform. Yeah. But it's consistent with all of them being similar, like equal or have a really, really small mass difference. Now, because the inferred chi effective is low, so it seems like many of them have low spin. On the other hand, so the inferred merger rate at least in the low Z universe is like 10 to 100 per cubic gigaparsec per year. So this means that in a major galaxy, this happens, for example, in Milky Way, maybe this happens every 10 to the 5 to 10 to 6 years. So this is still 3 to 4 orders of magnitude less frequent than core collapse supernova. So it's a rare phenomenon. It's not like super, super common. But however, because there are so many massive stars ending up with so many black holes, many of them are binaries, so we actually require just 10 to the maybe 10 to the minus 3 efficiency to make them if we use the field binaries. This is an estimate. In special environment, actually, we need much higher efficiency because the total number of stars we expect from this special environment is much less. Yes?
In terms of the field binaries that are being used, is that from, say, stellar binaries at similar mass ratios? Just because it's like we don't have binary black holes in our galaxy.
Yeah, so I guess here the assumption is that if you have a pair of massive stars, then very often they have comparable masses, like they don't have huge mass ratios. So we assume that as long as they can merge within Hubble time, they can make a candidate for LIGO source. And finally, so as I said, we are already probing binary black hole mergers not in the local universe, but in the past at cosmological redshift. So because of this exciting discovery, so a couple of people at the IES, we form a group who try to do something more like data-driven. We want to analyze the publicly released strain data. So basically our group have 5 people. I think lately there's a new student joining. So Barak and Teja, they are IS postdocs just like me, and then Matthias is a professor, and then Javier is a student working with Matthias. But none of us actually had background in gravitational data analysis before. So we do this because for several reasons. One is we are just really very curious of this new field of astrophysics. So we want to do something. And second is we want to see whether or not astrophysicists really have to rely on the experimental collaboration to tell them what are the properties of these sources, or they can actually do something with the data themselves. How accessible data analysis is to ordinary people, we are curious. And then finally, I think we are also curious in the question like how reliable their results actually are. Is it worth that someone outside of collaboration should double check on their results? So here is so basically we analyze data, public available data from the 2 LIGO detectors from 01 back in 2016. To early 2017, and also 02, which for most part is just 2 LIGO detectors. But then for the last month, when they suddenly started to detect a lot of black holes, the Virgo detector joined. So so far these are the publicly released bulk data that we can analyze. As you already know, currently they are doing 03. And 03 is made of 2 parts, 03A, which has finished in September, and then currently is 03B. So in 03, I think they typically have, for majority of the time, they have coverage from all 3 detectors. So some basics of gravitational signal detection. So in gravitational waves, it's different from other signal detection in astrophysics because the signal we're looking for is really, really faint. On the other hand, we have theoretically very precise knowledge what the signal should look like. So in this case, we should do the thing so-called match filtering in order to find out this weak signal from the data. So the idea is very simple. You take this template, strain as a function of time, and then you try to match, take some kind of inner product between this and the data. And then you slide the template as a function of time. So then you can compute this kind of overlap. So whenever there's no signal, this number is just some random small number. But whenever there is a signal, then this overlap suddenly becomes very large. So you see that there's a signal. So this overlap is not some naive overlap because the noise is the detector noise is not white. It is colored, which means that if you plot the power spectrum density, it's quite structured. So here I give an example of at some given time the PSD of 4 gravitational wave detectors. So you can see that basically you have some continuum, which is very noisy at both low frequency and high frequency end, but gives you good sensitivity within some optimal range. And then on top of that, you also have very narrow spectral lines. So now the way you do it is very simple. So for any gravitational wave template, you always have some trivial degrees of freedom. So for example, you can rescale the amplitude as a function of distance. You can change the time. You slide it in the time domain. You can also add a constant phase because the gravitational wave source is circularly or has a circular polarization. So depending on the orientation of the detector and the orbital phase, you can have a constant phase adding to the signal. So these trivial degrees of freedom can be captured by saying that let us always just normalize the template to 1. And then I compute this overlap of template with data. And I define it to be some complex number z. So this is a complex number. So basically, if the noise is perfectly stationary Gaussian random noise, then you can show that the z, this complex variable, the z mod square, should satisfy some chi-square distribution. So then the rule of the game is basically you compute this for every time, and then you make a distribution. It should agree with chi-square distribution, and anything that stands out of the tail, meaning that it's something interesting.
Quick question, if you go back to the previous slide before this, looking at the source, go back more slides.
Oh, one more.
Power. I was curious with all the extra stuff on top of that. Is this effectively just like experimentally determined what
Yes.
the frequency of different noises?
Yeah, so some of the lines are due to electronics. For example, you can clearly see the 60 hertz power line here. And some of the lines are like due to resonances of the this mirror, yeah, and also the cavity. Yeah, so many of them, they do have physical origin. Yeah.
Curious, and other people have asked this, like if there's anything you can extract from geophysics of the Earth.
Yeah, this is often people ask this question, can you study seismology using LIGO? So I remember one LIGO person gave an answer. He says it's actually the opposite, because they don't want seismic noise to affect their detector. So they designed the pendulum such that it is as insensitive to seismic waves as possible. So actually, that means that you can, if you instead use a normal instrument to measure seismic activity, is actually much more sensitive to LIGO, because LIGO don't want sensitivity to seismic waves. And also seismic waves, they are dominating mainly at low frequencies, but at high frequencies it's some other source.
So for a lot of the electronics stuff, in terms of that noise, would it be expected that is Gaussian distributed?
Empirically, it's very Gaussian. Yeah. Perhaps due to central limit theorem. Okay, but this is an idealistic picture. You have this chi-square distribution. Everything sounds very simple. In practice, we found that the distribution is very bad. So it's bad for several reasons. One is that sometimes the detectors, they make non-Gaussian noise, very swift but very loud. So these are called glitches. They come in various types. And some of them, we know their physical origin, either instrumental or electronic, or some pecking ravens. But sometimes, for some type of them, the physical origin is unknown. But one thing we know is that all of these things, they show very weird behavior in time frequency spectrogram, and they don't have any correlation between different detectors. So they cannot be gravitational waves. So then to treat them, we basically we use some criterion to detect abnormal power as a function of frequency. And once we find such a thing, because they are very swift, we just mask them out, saying that this second is bad, I cannot use it. But then we have to do this very carefully. The reason is that the matched filtering, this so-called whitening filter, basically 1 over the square root of this PSD, it's not a local kernel in time. So that means whatever you do in the time domain, you make some mask. Once you whiten it, it starts to leak outside of the window. So it starts to corrupt everything else. So this, to tackle this, usually, for example, LIGO collaboration, what they do is they apply some so-called window function. So this window function is basically a smooth mask. You try to avoid abrupt boundary. Everything goes smoothly to 0. But then if the PSD only has this continuum, this works very well. But we know that PSD also has very sharp, loud lines. And these lines meaning that they have very long autocorrelation function. So when you have those lines, they actually leak out and they corrupt the data elsewhere. So what we do is we solve some more rigorous linear algebra problem. So this is analogous to, you have this CMB map, but then the galactic plane is not measurable. But then you don't want to show a map with this mask, so you try to fill in the data by making a Gaussian realization that is most consistent with elsewhere. So this is some similar technique. You solve some linear algebra problem that allows you to put into the whole something. And this something, of course, is cooked up, but it has the property that when you do this match filtering, you're sure that elsewhere you are not corrupted. So there's no artifact left behind. So just give you one example. So in this famous binary neutron star, we were very lucky that in Livingston, so there was a loud glitch happening. But then, of course, you see that it doesn't really affect our ability to detect this signal. We can still see it by eye, and we can measure the parameter pretty well. But then, if you just do a naive mask, you mask it out. Then you do remove it, but then you see that you create this kind of mess. So these are the effect of the lines at around 500 hertz. There's a line. So here is a demonstration of this in-painting method. So you remove the bad section, but everything else is healthy. Another major effect, turns out that very important that corrupts this tail is the so-called PSD drift effect. So it turns out that the assumption of stationary Gaussian noise is a bad one. So we have some empirical measurement that the level of the noise fluctuation actually slowly drifts on time scale of, say, order 10 seconds. And also the amount of drift is something like 5 to 10%. So this has this bad consequence. So this has a bad consequence that basically, when you assume incorrectly that there's a unique constant PSD and compute this signal to noise square, the Z square, you artificially get a tail at high signal to noise ratio because there you are basically you're underestimating the actual noise variance. So your signal to noise ratio doesn't really mean signal to noise ratio. So this is the error you make. So in order to solve this problem, we just say that you can compute this Z, right? So then you empirically every, say, few seconds you measure the true variance of Z. And then you renormalize your signal to noise ratio. So this is called a PSD drift correction. We find that this is actually very powerful. So in many cases, the red is the distribution corrupted by this effect. And after you do that, you bring the distribution back to chi-square distribution. And this is very important because imagine you have a signal here, right? So in this distribution, it won't stand out, so you will miss it. But when you do the things correctly, it will stand out. And also the next step is that sometimes you get a very loud trigger because you're matching your template with some glitch. There are still glitches that can survive our bad second rejection. They can still survive. There are always some fish that leak through the net. So then what we do is we divide the waveform into several parts. And then we check that if the signal-to-noise ratio is coming from each part as in an expected way, up to some expected scatter due to Gaussian random noise. And then we do this, we set some threshold such that we make sure false positive rate is sufficiently low. Yeah, so then these help us to further kill a lot of glitches. So for example, in some heavy bank, after you apply PSD drift correction, you still get a lot of glitches. So the tail is still heavy, and then after you do the vetoing, you can get rid of this tail.
So this here, what's the difference between doing this and just doing like a coherent, making sure they're coherent and correcting for the PSD?
Coherent.
In all the different detectors, right? Because
Oh, you mean this? No, this is single detector level.
Yeah.
So you don't ask the question: is there a counterpart signal in a different detector? Yeah.
I guess I want to understand. So the different parts, you're checking whether every part is consistent with theoretical expectation. But isn't it the same as adding up all the signal to noise?
No, you mean, so because for example, you expect a signal to noise 10, right? And then you expect that, let's say I divide into two parts. I expect this part should on average give me 6. This part should, okay, what is additive is actually signal to noise square. So okay, this should give me signal to noise square 60. This should give me 40. But in some cases, you find that actually here I'm getting 80, I'm getting 20 here. Then you have to ask the question, is this consistent with some Gaussian random noise? Because noise fluctuation can give you some scatter. So we set some threshold to make sure that we don't get a lot of false positives.
But this is already corrected with the PSD and with the glitch in painting, right? Because you can imagine that
Yes.
there's a glitch in the low frequency part of your signal.
Yeah.
And you can paint it, then you're...
Yeah, so this is after we do the PSD drift correction, get rid of bad seconds. Yeah, and then in fact, this is computationally relatively expensive, so we only do this to sufficiently promising triggers. We don't do it for every trigger.
You're just saying there's some new information by doing that.
It's some kind of consistency check. And I think if theoretically the noise is perfectly Gaussian, you don't need to do this because every information is just in the distribution. But we know that it's not the case. Many glitches, they survive because our glitch rejection is this thing is not guaranteed to be like always effective. Sometimes they just leak through. Yeah. Okay, so now, so those are about signal processing, and here another question is, because the gravitational wave signals we seek have a range of parameters, right? It's not a single parameter. So we have to construct a template bank, meaning that we need to have a discrete list of templates such that it has the property that we shouldn't search for the same template repeatedly. But on the other hand, we should make sure that every signal we are expecting can be captured by the template. So how do we construct this template bank? There are ideas in the literature. People can either do some geometrical placement based on analytic formula, or people do some stochastic algorithm. But here we do geometrical algorithm, but we have a more like general formalism that doesn't really restrict it to analytic waveforms. So the key idea is that, so when we compute this overlap, we always do it in Fourier domain. We transform to the frequency space. Now this h of f is a complex number as a function of frequency. And then you can decompose it into a modulus and a so-called unwrapped phase. So unwrapped means that you make sure that the phase as a function of frequency is a continuous function. So if it wraps around 2 pi, you unwrap it. So then the realization is that this amplitude profile is not really very constraining, because even if you make some small mistake in the amplitude, you will reduce the signal-to-noise ratio a little bit, but you don't lose a lot. But this phase is really important because of this wrapping around. It's oscillating fast. So if you make a small fraction of a radian, you immediately lose the signal. So that motivates us to basically try to construct some linear basis function in the space of these phi f's. Imagine all of these curves, they live in some functional space. We try to construct a linear basis. So the idea is that, so there are 2 trivial bases. One is just a constant. One corresponds to a shift in time. But then everything else is some non-trivial information. So then we basically say that let's find some basis function such that it satisfies orthonormal relation, this one. So you can see that this depends on your expected amplitude profile of the signal and your noise curve. So it's a well-defined problem. You can numerically compute these basis function. Then what we realize is that typically within some parameter range that this A of f can be considered almost constant. You only need, for the phase basis, you only need something like 2 to 3, at most 4 bases. So the dimension of the linear space is not really high. So this allows you to basically make a rectangular grid. And then these coefficients, the range of these coefficients tells you where you should put this grid. The grid spacing is required by saying that for any physical waveform, I need to have at least one waveform in a template that has at least a 95% overlap. So this sets the spacing. So here, but we because we make the assumption that all the amplitude profile is the same, and this is only true in some local region of the parameter space. It's not true everywhere. So that's why we divide the parameter space into many banks, so-called banks. So these BNS, NSBH, BBH are artificially divided, but then in each range we make several banks. Now,
These are all non-spinning. These are all non-spinning.
no, they are spinning. So we actually include, spin. The dimension of a spin is not shown here in this plot. So why do we make these banks? So first of all, we really make this convenient choice so that this works. And second reason is that in fact, the number of templates vary wildly from here to here. So for example, here we only have ordered, say, 10 independent templates, but here we have ordered 100,000 or even 1,000,000 templates. So because the noise background, roughly speaking, is proportional to the number of templates. So imagine you have prior knowledge that many of the astrophysical sources are living here. Then searching here is unnecessarily like creating a large background. So that's why we divide into banks. So, and then we check that in each bank the match is always good enough so that we don't lose signal-to-noise ratio. Another problem we solved, which is not only useful for data analysis, real data analysis, but also useful for theoretical work, is to evaluate how to quickly evaluate the likelihood. So the likelihood formula is very simple. You just need to overlap this thing many times. And naively, you need to sum over many frequency components on some frequency grid. But when the duration of the signal is long and the sampling rate is high, the number of frequency can explode for example, in order to analyze double neutron star mergers, which could last for tens of seconds, even 100 seconds, you might have 1,000,000 frequencies. So this is the bottleneck. Just summing over these 1,000,000 terms is very slow. But then we solved this problem by realizing that if all you want to do is parameter estimation, then you are not like blindly looking everywhere in parameter space. You are only looking near some good fit. So when you are near some good fit, even though the waveform, each waveform as a function of frequency is oscillating rapidly, so you need a very fine grid. But the ratio between two different waveforms is a very smooth thing. So you just need a very sparse sampling. So then the algorithm is basically you pick some fiducial waveform, which you can know, for example, you can get it from your search pipeline, and then you compute this ratio with rather low frequency binning. And then you pre-compute some moments. And these moments you just computed for the fiducial waveform, and you compute it once. And then as you explore many, many points in parameter space, you repeatedly evaluate this thing, but you sum over bins. You don't sum over individual frequency. And the number of bins can be as few as only 100 instead of 1,000,000.
So how sensitive is this to the goodness of the bit of H naught?
H naught.
You said 0 here. How sensitive is this to how good of a fit you get from your search pipeline when you're doing parameters?
Yes, so in fact, it's a very easy thing to, even if the first H naught given to you is not good enough, it's very easy to just first go up the likelihood a little bit, and then you will find a much better fit, and then you use that as your new H naught.
So you're updating.
You iterate a few times, but it turns out that it's usually that one iteration is enough. So the H naught is good enough. So how do you know it's good enough? So here in this example, so this is again this binary neutron star we use as a demonstration. So you make these frequency bins. They don't have to be uniform. We have some optimal choice for these bins. And then you just need to make sure that the exact likelihood, which is this horizontal axis, the difference between exactly likelihood and your approximate formula, which is this, in absolute units is small enough. So here, for example, we think that as long as you can make it smaller than 0.1, then it essentially makes no difference in parameter estimation. So this turns out to be extremely useful, and now we are using it routinely in our analysis. And it's also if you want to do some theoretical work and you want to do some mock analysis, then this is a very simple thing to code up and very efficient.
I just have a quick question about this likelihood plot here. It looks like with however many bins, these are the number of frequency bins you have. Looks like it's fairly well contained in all the points. Is there a good reason for that?
You mean why they are this wedge? Oh, the wedge is easy to understand because, so this is the highest point which we choose as the fiducial waveform. So by definition, the error should be 0 here. And the further away you're from this H naught, then the more error you're making.
So does that mean that if you have some threshold for...
Yeah, you just need to make sure that you first have some threshold here, because in parameter estimation you never explore very far here, right? Because it's a much worse fit. So let's say 10 points from the best thing. Here you make sure that your error is less than something.
I guess my question is then, can you use that to get sort of an optimal number of frequency bins before you do the calculation, or no?
I think, yes, there's room to optimize. Although in this choice, this division is, it's not making use of the knowledge of your signal to noise ratio. So this division is only about what what are all the possible phi of f's? You know, I can write phi of f as a function of as a sum over many terms. Each term is f to some power. So I only make use of this information. Yeah. So, but there is room to optimize. We just find that this thing is already good enough, so we didn't.
Anything up that much of like the difference between 60 bins versus.
I'm sorry.
Great.
Actually, it's important because it's linearly proportional to the number of bins. So if you double the number of bins, you are twice slower. Yeah. So,
I asked too many questions.
no, it's fine. I think everybody is welcome to ask questions. How can I get it back to live? Okay. Yeah. So now, so far, I have talked about how do we find interesting triggers at the single detector level, right? So then one way we find genuine gravitational waves is to look for coincidence between different detectors. So if you have genuine gravitational waves coming from the sky, then the delay between the two detectors is at most 10 milliseconds. This means that if you artificially slide one detector relative to the other by more than this amount, then whatever coincidence signal you're finding must be due to noise. So this actually gives you an empirical way to measure the noise background. So it's very robust. You make the minimum number of assumptions. So this is called coincidence analysis. So we find genuine signals that exist in multiple detectors. So in this way, we analyzed the O1 and O2 data. So in both data sets, we find something interesting. So first of all, this O1 data sets. So originally, LIGO's pipeline reported, in addition to the two events, they reported LVT. So they were not very sure of that, but they think it's interesting. It's very interesting. So in our analysis, we basically find that this is definitely real. The significance is very high. And then in addition to that, we find some new candidate, this 15, 12, 16. So what is special about this is that our parameter estimation suggests that the chi effective is very high. So this has not been seen before. So we reported this as an interesting candidate. And then through parameter estimation, we also find some very interesting thing that people maybe should be careful about, which is, so for this event, at the first we use LIGO's spin prior. So so basically this prior assumes that the two spin vectors, they are isotropic. They take random directions. But then this has a consequence which makes a prior for this chi effective parameter that peaks highly at 0. And it artificially kills any solution that has high chi effective. But then we realize that there's a problem because we find that although we get some nice posterior, the best fit, the maximum likelihood solution actually lies beyond the 2 sigma contour. So it's a sign that the prior is doing something fishy. So then we instead use a flat prior. And then we find that the spin is even higher, is approaching the maximum value. So from this, we learned that basically for those low spin events, this doesn't make big difference. You will always get something here. But suppose in the future you discover some high spin events, this prior actually plays some role. So people need to try both.
We analyzed everything basically in the first 2 runs, right? And what fraction of the mergers with the flat chi effective prior have a chi effective significantly different than 0?
We only found, I guess, 3. I mean, this is a very extreme example where
Yeah.
it's almost close to 1. Out of, we have 6 from 0 well, we have 6 and this is 1, and then we have 2, 1 that are detected in a slightly different way. So I would say 9 in total. Yeah.
And the other 2
They are not so high. They are like,
are like 1 sigma away from 0 or?
yeah, they are kind of not very consistent with 0. Yeah. But I guess, this event needs to be verified, but this prior effect, I think people didn't know it before. It's actually quite subtle.
So is there astrophysical motivation for a flat prior on trifecta?
There is definitely, well, I would say there's definitely motivation to try both because...
No, I agree with you. I'm just thinking of...
what a model.
Yeah, the evolutionary scenario that would give you...
Well, the reason we pick this is basically we just say let's not try to artificially disfavor any value. But I would say if you have field binary evolution, then it's more likely that the spins are aligned. But of course, the probability may not be flat. And then there's another interesting thing is then we are, because this event is kind of special, we are double checking this with the MIT LIGO-Virgo group. And then they reported some inconsistency. They said if you use this flat prior, you get some high spin. And if they use the isotropic prior, it shifts to lower values. But then they're saying, as opposed to in our case, we kind of exclude 0. In their case, they have a tail that is consistent with 0. So they say it's still consistent with 0. And then we track down to the trace of this disagreement. And then we find that the reason is that for some reason their signal-to-noise ratio is systematically lower. And then we realized that it is because they are using different power spectrum density in the likelihood as we do. So here I plot the difference. So basically what we are using is we measure PSD on very long time scale, so that allows us to resolve all of these thin lines, so the green things that we show here. But then what they have is they use something called a baseline. So baseline is some more sophisticated way using, it's a Bayesian way to tell you what is the best estimate of this PSD. And then they say, because we are not very confident that the noise model should be the same across hundreds of seconds. So they choose only to analyze 4 seconds. But then, by doing that, they are unable to resolve these thin lines, right? Because your time window is so short. By definition, you cannot resolve very thin spectral feature. So then, the blue line is the PSD their software spits out. But then, after we do this comparison, we are very confused because you can see that this broadening of line is understandable, but then the continuum is also, their continuum is very simple and lacks all these features, all these bumps and so on. So what's going on? And then we realized that the way they are doing things is they have some parametrized model for this curve. They have some spline, and on top of that, they add an indefinite number of spectral lines. And then they do everything in a Bayesian way, try to find what is the best answer. But then we really have issue with this, this way of doing things. So we want to show that this 4 second is really problematic. So it turns out that we think that the reason they are losing signal-to-noise ratio is by the time you choose to analyze noise on 4 seconds interval, because of these strong, narrow spectral lines, your noise covariance is inevitably off-diagonal. So we demonstrate this by basically we start with 64 seconds, And we believe it's long enough to resolve these lines. And in that case, we can start with a diagonal covariance matrix. But then we restrict to examples of these 4 seconds and ask what is the induced covariance matrix. You can see that it's almost diagonal, but whenever there's a spectral line, you have these spikes. You have all diagonal elements. So this is just zooming. This is just zooming into the neighborhood of 60 hertz spectral line. And then our evidence that this model is doing better than their model is basically if you evaluate the chi-square. So this model is basically, in terms of chi-square, it is a factor of 1,000 units better. So it's basically, from the Bayesian point of view, it's a much better description of the noise. So we think this can be problematic. This fault is not so important when the signal-to-noise ratio is high, because when it's high, this little drop-off doesn't really make a big difference. But in this case, we just happen to find that it makes some difference. So then for the O2, we find 6 more black hole events. So you can see that.
Out of curiosity, do you have a sense of what the sort of threshold signal-to-noise ratio is for how you're treating the PSD with matter?
So all of these events, you can see this is so the total network signal-to-noise ratio is about between 8 and 9, 8 point something. So this is our level of threshold. So things below that is buried under the Gaussian background. So, I mean, in terms of this number, it's just slightly lower than LIGO's number. For example, they are limited to, say, somewhere between 9 and 10. So we just improved that by like 1 unit. But it turns out that this 1 unit corresponds to almost like a factor of 2 increase in the volume. Because the volume scales as distance cubed. Yeah. So now we detected 6 events, and 3 of them we think are very confident because, first of all, the false alarm rate is really good. And second of all, we compute something called P-astral. So P-astral basically is how likely it is a gravitational wave relative to its noise. So for these 3 events, it's like high enough that we are confident. But then for the other 3 events, the far is interesting, but then the P-astral is not great. So they are kind of borderline. But then I think very recently, so Nitz et al., they published a so-called 2 OGC catalog. So in their analysis, they also reported new detections with completely different independent pipelines. And then they report that the 3 most significant new events they report are the 3 that we have. And then, of course, the other 3 are also on their list, but not, they also have something else. So at least, some of the events are confirmed by a 3rd group.
So their P-astros are significantly lower than your P-astros?
Well, for this event, for this one, it's good, right? 999.
Yeah, but for the other ones, these are significant.
Yeah. For the other ones, they somehow judge that it's not significant. But of course, we know that the conclusion about significance is pipeline dependent, right? Because if your pipeline is very bad, then you cannot detect anything. So so these numbers are not some astrophysical number. Yeah, it's.
17 or 77, they actually give a higher P-astro than.
Yeah, that's true. Yeah, this one they.
0.98.
Yeah.
It's not that much.
Yeah.
The growth of these results, they're different ways, like it's calculating P-astro in different ways? Or
In different ways, yeah. Yeah, I would say this P-astral is more uncertain because even though the noise hypothesis is well defined, the astrophysical hypothesis is not, because you need to assume some model for the sources. What are their mass distributions? What are their distribution in volume, right? right? So those actually we have some detections, but we don't really know them precisely. So yeah, how many minutes I still have? I think I'm kind of running out of time already. But maybe I will just mention very quickly. Let me see. I don't have a lot of slides. Yeah. So yeah, let me mention very quickly. So apart from this coincident analysis, there's another situation, which is sometimes one detector has a loud signal-to-noise ratio. The other detector has a very marginal signal-to-noise ratio. So in this case, this kind of trigger can fail to be collected because we always need to set some minimum threshold to collect the trigger. So for example, in 03, their first binary neutron star event is of this nature. As we reverse engineering, of course they didn't say, but we think that this is the case. There's a loud signal in Livingston and there's a very marginal signal in Virgo. So then in this case, we cannot really do the false alarm rate calculation in the usual way because this detector has almost no signal, right? So we cannot even collect all similar triggers. So then we do some other way, which is basically we test the two hypotheses. One is that this is just random noise. The match you find in the other detector is just random noise. The other hypothesis is it's a genuine gravitational wave. And then we basically marginalize over all extrinsic parameters. We define some score, and we can Monte Carlo these, the distribution of this score under these two hypotheses. So we tested this with one of LIGO events, 1708-18, which was announced by using all three detectors. But we show that basically using this method, we can declare it by just using two LIGO detectors. Because in this case, Virgo has, we didn't use Virgo, and Livingston has 10 sigma, and Hanford has more than 4 sigma. So in this way, we can show that that's enough. And then we ask, are there other events that can be declared in this way? So we found that two events that are kind of marginal. So all of them have some kind of good false alarm rate, but on the other hand, the distribution for the astrophysical hypothesis is also kind of fine-tuned. But it's kind of expected because anything that is not fine-tuned is already discovered by this coincident analysis. So I think what is interesting is this event that it shows that the mass is really heavy. So this event. So in a detector frame, the chirp mass is almost 70 solar masses. So translating into the source flame, each black hole, the heavy one is at least, I think, more than 50 solar masses, something like that. And then we put together everything on this plot, total source frame mass and effective spin parameter. And so the blue are LIGO detections, and other colored ones are our new candidates. Some of them are very secure and confirmed by other teams. Some of them are less secure. But just from this, we can see that indeed they're very heavy, much heavier than X-ray binaries. So the question is, is the abundance of things here consistent with the power law or not? So this is so far I think it's still consistent by doing statistics, but more detections will give better constraint. And also, but on the other hand, we don't see things beyond like 50 solar masses each. So far consistent with this pair instability supernova prediction. It's also consistent with the comparable masses, and most of them have zero spin, but we kind of see some trend, which we don't really know if it's true or not. Is once you go to higher masses, it seems that the spin systematically goes to like positive, non-zero and positive. So of course, this needs to be verified with more detections. Yeah, so.
You say consistency with pair instability supernova. you're equating the black hole mass with the helium core mass? Or what? Because a 50 solar mass star in itself doesn't produce very stability.
The progenitor definitely needs to be much more than 50 solar masses. I think it's more like 200 solar masses. Yeah.
How much collapses.
Yeah.
Assume we have a density profile shift.
Yeah, I think it's not. Yeah, I think the number they're talking about, the progenitor star, is like 200 solar masses, and then you shed some mass, and then below this limit you can still end up with a massive black hole. But then above this limit you become too unstable and just completely destroy itself. So this is the picture. Okay, I think I'll just leave my summary slide.
How long will it be before we convincingly measure spin-orbit interaction in the INSPIRE?
It's a very weak effect. So currently, you mean the spin, the wobbling, right? Yeah, so this requires that the two spins are not aligned.
But assuming that they are.
Oh, assuming they are.
Assuming they are not aligned.
They are not. So far, people do analyze them, but my feeling is that at this signal, at current signal-to-noise ratio, it's not really detectable.
Will it be possible at design?
So at the design, most of the events are still of this signal-to-noise ratio, but there will be some minority of them will be louder because they're nearby. For those, there's a hope, yes. Yeah, because currently people do fit for precession solutions, but they usually find that the fit is better because it has more free parameters, but it's not significantly better. Yeah.
So you said that according to the data, it seems to favor, it seems to observe a cutoff of 50-something solar that's Does this mean that this favors dynamical capture, right? Because dynamical capture won't care about this limit.
Even our thing. So okay, I mentioned this 50. The massive component is at least the more massive component is at least 50, and also there's a rumor that LIGO in 03A detected a system whose total mass is more than 100 solar masses. So similar to this one, but even I think in both cases they could be just at the cutoff, because I think the theoretical prediction they say is that so on the one hand, you don't have anything beyond the certain masses. On the other hand, just a little bit below this cutoff, you have a pile up. But exactly where this cutoff is, I think currently paper quotes anywhere between 40 and 55, but it's not narrowed down to like a very precise number. So I would say this, because you also see that the error bar is huge, right? So I would say this event, even though it's heavy, it doesn't rule out. I think it's not necessarily a counter example.
Okay, we can have the discussions after.